In the last video, we looked at special segments of a triangle. In this video, we'll look at points of concurrency. Points of concurrency are where you have three or more lines that meet together to form one point. So if you notice, these lines are not concurrent because they don't meet at one point. These lines are not either because they don't meet at one point. And these lines would be concurrent because they meet at this one point right here. Two other important vocabulary words for what we're about to learn are circumscribed and inscribed. This would be an example of a circle circumscribing around a triangle. The triangle is inside and the circle is going along the outside. And this would be an example of an inscribed circle because the circle is inside the triangle. It's touching at one point on the sides of the triangle. If you notice on the circumscribed circle, the vertices are each touching the circle. So let's go ahead and explore these points of concurrency and the special segments that we learned in the previous video. So let's start by looking and see what happens when we get our medians. So here I have my triangle, and I'm going to go ahead and show my medians. If you notice that when you do all three of your medians, they meet at one point called the centroid. The three medians intersect and create the centroid of a triangle. And the centroid is pretty interesting because it actually creates the center of gravity. That's an example I've shown in classes. If you actually cut out a triangle out of some cardstock or cardboard, and you find the medians, the three medians, connect them to get the point of concurrency, which is the centroid, of course, you can actually balance that piece of paper or the cardboard just using a pencil or a pen. You actually just stick your pen or your pencil on that one point, and it balances perfectly for you. So the median is actually highly useful in finding the center of gravity. No matter how the triangle spins, you'll notice that the centroid will remain within the triangle. So even if I have a right triangle or an isosceles triangle and equilateral, the centroid is going to stay within the triangle. If I connect my three altitudes, I get what's called the orthocenter. And the orthocenter is sometimes going to be inside. If it's a right triangle, it'll be right on the vertex, the right angle. And if I spin that triangle and I create an obtuse triangle, the orthocenter will actually be on the outside of the triangle. So let's go ahead and get that back to acute because those triangles look a little more familiar. There we go. And our acute triangle will be on the inside. The angle bisectors, when joined together, will create the point called the incenter. The incenter is actually a nice little point that we can create an inscribed circle from. That point will be equidistant from all the sides of the triangle, whether it's a right triangle, an isosceles triangle, equilateral triangle, or even if you get an obtuse triangle, you can see the incenter stays inside the circle because, well, it's the incenter, it's inside, created by the angle bisectors. And the final point of concurrency is what we call the circumcenter. The circumcenter is created by connecting the three perpendicular bisectors of the triangle. If it's a right triangle, the circumcenter will be on the hypotenuse. Isosceles, equilateral will be in the middle. An acute triangle will be somewhere inside the triangle. And an obtuse triangle, the circumcenter will actually lie on the outside. Now what's cool about the circumcenter is that the circumcenter creates a circle around the triangle is circumscribed. It circumscribes the triangle, and every vertex of the triangle will be equidistant from the circumcenter. And the Euler line is actually just a little bit of trivia. The orthocenter, centroid, and circumcenter will always fall on the same line. They'll always be collinear and form what we call the Euler line. All right, so a way to memorize what each of these goes with is, okay, actually, let's go back. I want to show you real quick what happens when we have an equilateral triangle. When you have an equilateral triangle, if I show my median, my centroid's there, my altitude, so my orthocenter is there, my incenter is at the same point, and my circumcenter is at the same point. So in an equilateral triangle, all of these points are actually the same point on an equilateral triangle. In an isosceles triangle, they're very similar, and they'll actually be collinear as well. Okay, now let's go ahead and go back to a little acronym to help us memorize these points. all of my classes are bringing in peanut butter cookies. In other words, when I have my altitudes, the A, I get my orthocenter. When I have my medians, M, I get my centroid. When I have my angle bisectors, I get my incenter. And when I have my perpendicular bisectors, I get my circumcenter. So it's a little acronym that you can use to help you remember what each of these go with. So what about these? Let's review one more time. The circumcenter is the point that is equidistant from each vertex. So if I want to find the point that's the same distance from all three vertex, I find my circumcenter. The incenter is equidistant from each side. So if I'm trying to find a distance to each side that's the same, the incenter is the way to go. And the centroid is the center of gravity, as I talked about with the triangle. You can make one as this girl here did in this picture. Something else about the centroid is that the medians of a triangle are concurrent, so that's the definition. And that point of centroid, so point C would be the centroid, it's actually going to form a ratio. So DC, this section here, equals 2/3 of the whole line DJ. Same thing when you look at GE. CE would be 2/3 of the whole line. And same with FH. FC will be 2/3 of the whole line. So let's say D is the center of triangle ABC and DE is 6. Well, let's see. DB will be 2/3 of the line, so DE has to be 1/3 of the line. So if this is 1/3 of the whole line, we know that 6 is 1/3 of 18. So all of BE will be 18. And one last thing to look at, some examples. Let's say the first aid center of Mount Thermopolis State Park needs to be at a point that is equidistant from 3 bike paths that intersect to form a triangle. Which point of concurrency is located at the point so that an emergency medical personnel will be able to get to any one of the paths by the shortest route possible? Now, paths would be the size of the triangle, so you would use the incenter to be able to find the shortest distance to the paths. The next one, Julia Child wishes to center a butcher block table at a location equidistant from the refrigerator, stove, and sink. Which point of concurrency does Julia need to locate? Well, she wants to be equidistant from the 3 vertices of the triangle, because those 3 shapes would make the vertices of the triangle. So the point there would be the circumcenter. And finally, which point is the center of gravity of the triangle? Well, we know that that is, of course, going to be the centroid.